Hello everyone. So let's finish this discussion with polynomial and rational functions. We are in our last section. We're going to talk about complex zeros of polynomials and an important theorem of algebra, namely fundamental theorem of algebra. So far, up until this point, we found real solutions or zeros of polynomial functions. Again, the key word I want to emphasize was real. We found real solutions. This time, in this section, we want all zeros, including complex zeros. Okay, so before we actually get going here with complex zeros and the fundamental theorem of algebra, though, I guess we do need to do a quick review of complex numbers. So I just like to do that now. If you remember, complex numbers are numbers that have two parts in the form a plus bi, where I is called the imaginary unit, square root of -1, so that I squared is -1. The other unique or distinct powers of I are I cubed, which is -I, and I to the fourth, which is 1. Now, the work that we are doing in this section, we are primarily interested in I and I squared. Okay, so for example, a number could be 3 plus 4i, and that's a complex number. It could be 2 -i, that's a complex number. Or I could have simply a number 7i. In the case of 7i, because the real part, that's what a is called the real part. And the bi is called the imaginary part. Because the real part of 7i is 0, then the number is called pure imaginary. So the numbers that are in the form bi are called pure imaginary. Okay. Now it's interesting, we can work with these complex numbers, and let's go back to, for instance, the case where we had square root of -4. If you recall square root of -4, when we talked about the real answers here, we said simply it's not real, which left the door open for other types of numbers, namely complex numbers, to be the solution of these. So I can further work with square root of -4, write it as -1 times square root of 4. Well, square root of 4 is 2, square root of -1 is I, and we can write that as 2i. That doesn't make square root of -4 real, though, but however, we can write it in an alternate form. Okay. Now, when it comes to complex numbers, we can add, subtract, multiply, and divide them. So their addition and subtraction is pretty easy. You just combine like terms. So for example, let's say we want to add 2 minus I plus 7 plus 3i. You add 2 and 7, we get 9, and you combine 3i -i, we get 2i. So addition subtraction is pretty straightforward, but let's take a look at the product now. Suppose I want to do 3 minus 5i and times it by 4 plus 6i. To multiply them, we FOIL them, correct? So we're going to distribute 3 to 4, we get 12. 3 by 6 is 18i, and then do the same thing with 5. -20i, -30i squared. All right, and we have those. And then we can combine like terms. 18 minus 20, that's -2i. And then -30, remember I squared is -1, right? So I can write that as -1. Okay, and then that makes the last number real. So this would be 30 and 12, that's 42, -2i. And there is the product. That's how we multiply complex numbers. Okay. Now, let's talk about complex conjugates. Two complex numbers are conjugates if we can write if one of them, for example, if one complex number is a plus bi, its conjugate is a minus bi. Notice they have the first term, same last term, if you will. The only difference is plus and minus here. So these become conjugates of each other. As an example, conjugate of 7 minus 5i This one is going to be 7 plus 5i. Conjugate of 8i is negative 8i because the real part is 0, a is 0. So notice you only change the sign on the imaginary unit for conjugates. All right. Now if we work with real numbers, by the way, let's say I want complex conjugate of number 15, which is real. Now 15 as a complex number, the real 15 as a complex number could be written this way, right? 0i. What's the conjugate of that? 15 minus 0i. But then 0i is just 0. So conjugate of real numbers are themselves. But we don't talk about conjugates of real numbers often. Hardly if at all. Okay, now we did talk about complex conjugate of pure imaginary numbers, and we talked about the general complex conjugate of complex numbers in the full general binomial form. Now let's look at the product of two conjugates. Suppose I have 8 plus 3i and then multiplying by 8 minus 3i. These are clearly two complex conjugates. Now let's do FOIL. 8 by 8, 64. 8 by 3. 8 by 3 would be negative 24i. I just did my first distribution. The F and the O, I'm doing FOIL method, right? First, outer, inner, last. That's what we're doing. The inside terms and last terms. So that's going to give me plus 24i and negative 9i squared. Okay. And then what do we do next? We're going to combine like terms. Now when we combine like terms, the OI add to 0. So all we have is just first and last. And remember, I squared is negative 1. That's times negative 1. And we have 64 plus 9. And that makes it 73. Right? Now here's how we're going to do this the fast way. This, by the way, happens every time when we multiply complex conjugates. The OI always adds up to 0 because they end up being opposites. And the product of two complex conjugates is going to be real. Real. Okay? So let's do this now the quick way. When we multiply conjugates only, we can do a shortcut. You don't need to do the OI. You simply do square of 6 plus square root of 5. Not negative 5i, just 5. So that's going to be 36 plus 25, and that will be 61. Okay, so this is how I tend to do complex conjugates multiplication. Now, let's talk about, so that's all the review we need for complex numbers. Okay, so let's talk about now complex polynomial functions. A polynomial function is called a complex polynomial function where it is structured exactly the same as before. And I want to also mention, by the way, the real numbers, if you recall, are a subset of complex numbers. So everything we do with complex numbers, with real numbers, we can do with complex numbers because real numbers are subsets of them. I kind of showed you one already, see 15? That's a real number, but we can write it as a complex number with a pure imaginary part, or just simply imaginary part being 0. So what is a complex polynomial function there? In this case, the a's, the leading, not the leading, but the coefficients are complex numbers. Okay, so the a's are complex. The n here is an element of the set of whole numbers. In other words, the n's are 0, 1, 2, and so forth. Okay, that's what the n's are. And x is also a complex variable. Okay, that's what that is. A sub n, just as before, a sub n is the leading coefficient. Okay, and there we have that one. Now, r here would be a complex 0. Remember, we talked about r being real 0. Now, r this time is a complex 0 if in that complex polynomial you plug it in and you get 0, just like before. That means x minus r is a factor, right? Just as before, a factor of f of x. All right. Now, next I'm gonna write down for you the fundamental theorem of algebra. Very important theorem. And this theorem was actually proposed and proved by Carl Gauss. I believe it was in the 1800 or late 1798, 99, 1800, on or about. And this was part of Gauss's doctoral dissertation. Okay, so I'm going to go ahead and write it down, and then I'll talk more about it with you. So here we go. The fundamental theorem of algebra. This theorem reads, every complex function f of x that has a degree at least 1, it must be a degree 1 complex number, okay? A complex function, can be factored into n linear factors. And these linear factors are not necessarily distinct. That means the theorem allows for repeated multiplicity of these factors, right? Of the form that, we've seen this form before, by the way, this form, remember? We saw it earlier as well, except now x is a complex variable and a sub n here is a complex number, and so are the roots, so are the zeros, if you will. And stated here, a sub n and the r's are complex numbers. So according to this theorem, thus every complex polynomial function of degree at least 1 has precisely and exactly n complex zeros. And again, some of these zeros may be repeated. So if you have, for instance, a 5th degree complex function, a complex polynomial function, then you would expect to see exactly 5 roots, 5 zeros. Okay, so that's pretty cool. The next theorem that I actually like, this theorem too, is, I'm gonna try to prove this one for you. This one is the conjugate pair theorem. The conjugate pair theorem, very important theorem for us. And we'll see example of these in just a moment. This one tells us that complex zeros occur in pairs. They have to appear in pairs. So here's how the theorem goes. Now what's important is what I have in green for this theorem. Okay, this isn't true necessarily for complex polynomials, but if f of x is a polynomial function with real coefficients, if r, which is a plus bi, is, notice by the way, this is a polynomial function, this is not a complex polynomial. Okay, so we just have a polynomial function. Now if r in the form of a plus bi, in other words, if one of the roots is a complex number, a plus bi, then so is the conjugate of that. Remember, a minus bi, a plus bi are conjugates. So r bar here, r with a bar, is the conjugate, right? That's conjugate of r, and vice versa. These are conjugates of each other. Okay, now let's actually prove this one, because the proof isn't that difficult. So for this one, let's say my polynomial is in the general form an x to the n plus an minus 1 x to the n minus 1 plus so on and so forth, all the way down to a linear and a constant. Okay, now a's here are all real. Okay, keep that in mind. The coefficients are real. So we are told if r equals a plus bi is a 0. That is the hypothesis of this theorem. We can assume that to be true because that's what we're told. See, if that is a 0. So if it's 0, then we take it to be a fact. Well, if it's a 0 of f of x, so what do we know then? Then we know that f at r has to be 0, correct? Because it's a 0 of the function. Well, what does f at r mean? Well, f at r, that's when you change your x's, right, to r's now. And that's what I'm going to do. So f at r means a sub n, r to the n, plus a sub n minus 1, r to the n minus 1, plus dot dot dot, plus a sub 1r plus a sub 0. Correct? Now, with equations, we can do just about anything provided we can do to both sides, right? We can add, subtract, multiply, take the roots, exponentiate, so on and so forth. So in this case, let's take the conjugate of both sides. So that's what I'm going to do. Take conjugate of both sides. Okay, so when we take the conjugate of both sides, this is what it's going to be. On the left side, conjugate of r is r bar, right? And what do we have on the right side? On the right side, well, the conjugate is going to be, let me actually, yeah, I'm doing the proof here. I was going to see, yeah, that's fine. Okay, so I'm going to take the conjugate of the right side. Sorry about that. Now, when I take the conjugate of right side, so that's the conjugate of the whole thing, the entire expression, plus a1r plus a sub 0, and I'm going to take conjugate of the entire statement here. Now, there are several properties about the conjugates of complex numbers. One of them says that the conjugate of sum will be sum of conjugates. Okay. Now, by the way, remember f at r was 0 here, right? So if I take conjugate of both sides here, then I have equal to conjugate of 0, right? Because I'm taking conjugate of both sides. Okay. And I have it here. F of r is 0. So we're going to set this equal to 0. Now, conjugate of both sides would be this. Now remember, 0 is a real number, correct? And conjugate of a real number is itself. So conjugate of 0 is just 0. And using properties of conjugates, again, conjugate of sum is going to be sum of conjugates. So I can write this as a sub n, r to the n conjugate, plus a sub n minus 1, r to the n minus 1 conjugate, plus dot dot dot, plus a1r conjugate plus a sub 0 conjugate. Cool? So conjugate of sum, sum of conjugates. Now, if we take the conjugate of this term, each term, we can use the product rule of conjugate. This is a constant multiple, so it's going to be conjugate of a product is product of conjugates. That's what property I'm going to use. This is a product of a sub n by r to the n. Conjugate of a product is going to be product of conjugates. So that's going to be a with a bar, conjugate of a sub n times r bar to the n. The next one is going to be conjugate of n minus 1 times r bar to the n minus 1, and so on, plus this is going to be conjugate of a1 times conjugate of r, plus conjugate a sub 0, right, equals 0. Now remember, the coefficients are real, right? The a's are real coefficients. So all of the conjugates that involve the real coefficients are just going to be the coefficients. So a bar, a sub n bar, the conjugate of that coefficient is going to be itself, and we can write this as r bar to the n plus next one would be a sub n minus 1, r bar to the n minus 1 plus a sub 1 times r bar plus a sub 0 equals 0. Now if you look at the left side is your f of x, where x is r bar now, isn't it? True? That's going to be the polynomial function evaluated at r bar. Therefore, the whole left side is f. Instead of x, put f at r bar. And we just showed that's equal to 0. Well, what's the implication of this? If f at r bar is 0, then this would imply that r bar is a 0 of f of x, right? That's by definition of 0 of a function. And what is r bar? Well, r bar is a minus bi. Therefore, we just showed that if r equal a plus bi is a 0, then its conjugate is also a 0. Very useful, very interesting theorem here. Okay. Now, now that we have this, let's take a look at, actually, before we look at examples, we're just going to look at a real quick corollary to this theorem. A corollary is a direct result of a theorem. So we're going to look at the corollary to what we just observed here. Complex, remember, complex 0 occur in pair if the polynomial has real coefficients. So here's what the corollary says. A polynomial function, call it f of x, of odd, okay, it's going to be odd degree. If the degree of the polynomial is odd, again, with real coefficients, has at least one real 0. So this is amazing. You can make up your own polynomial functions with real coefficients. Make them odd degree. So do a 3rd degree, 5th degree, and so on. Your function that you make up will have at least one real 0. Okay? And the reason is because, remember, complex solutions occur in pairs. So if it has odd degree, let's say, for instance, I have something like x cubed. Well, odd degrees could be written as x squared times x, right? Well, for the polynomial with even degrees, I could have complex numbers, right? They appear in pairs, the solutions, the zeros, that is. Therefore, that polynomial function will have at least one real 0. Okay? Now, let's finish off our work with some examples here. Okay, so all in all, we're going to look at about 4 examples. Now we have three or four examples. Let's see how this is going to work out. So in this example, let's say I want to find a 5th degree polynomial with real coefficients. In this course and in your calculus series, we usually do not work with complex polynomials. So they're all going to have real coefficients. So our focus is on real coefficients. So find a 5th degree polynomial with real coefficients whose zeros are 2, negative I, and 1 plus I. Okay, well, this is a 5th degree polynomial, so it's going to have 5 zeros, correct? Therefore, if r is equal negative I, remember its conjugate, I has to be also a solution because these have real coefficients. And we just said the corollary directly above what I have written here. The corollary says that complex solutions, well, actually right up here, the conjugate pair theorem, this theorem says that complex solutions occur in pairs and they have to be conjugate. So there you go. Here's the other 0. Call it R1 and R bar 1. The other complex 0 we are given is 1 plus I. Therefore, its conjugate has to be a solution, and those are the 5 roots of this 5th degree polynomial. Now, for simplicity, always we let the leading coefficient be 1. You can let it be anything. So the answers here will not be unique, but let's agree to let the leading coefficient be 1. So the solutions, and remember earlier what we set up here by fundamental theorem of algebra, those are the factored form of the polynomial. Okay, and I know it's complex, but it also works with non-complex polynomials. So f of x is going to be x minus c, x minus the root. Next one would be x minus I, x plus I. That's when you do x minus this root and x minus that root, and then x minus this one, which is 1 plus I, and x minus its conjugate, 1 minus I. And there you have it. That would be the complex, those are the complex roots, and that would be the polynomial with real coefficients. Now, because we want to know what the polynomial function looks like, we have to carry some of these multiplications. Okay, so here's how we do this. Keep the real factor away from this. In here, I'm multiplying 2 conjugates. And remember, only when you multiply conjugates, you can actually square the first term plus the constant squared. That would be 1 squared, which is 1, right? Or you can FOIL it if you want to do that, but I wouldn't recommend it. We did this earlier, and I showed you that 2 complex conjugate, you just do a squared plus b squared, right? So that's how you get that one. When we multiply this one, let's do that one separately. Okay, when I multiply this, I'm going to distribute x times the binomial, and then the complex number times the binomial. So x times x, that's x squared, negative x times 1 minus I, negative x times 1 plus I. I just did this part. And then finally, negative times negative is going to be plus 1 plus I times 1 minus I. Okay, so there, we just did FOIL in here. Let's carry on. This becomes x squared minus x plus xi. Next, I'm going to get negative xi, right? Plus, and then again, we are multiplying 2 conjugates. When we multiply those 2, what are we going to get? You square the first one, you square the second one, the coefficient on the second one, which is a 1, right? This is just I, so this coefficient is 1. So you're going to get plus 1 squared plus 1 squared, right? Again, that's because I times negative I gives you negative I squared. That's where this one comes from. All right. And let's simplify this work. Negative xi, those are opposites. So this becomes x squared negative 2x plus 2. And that's going to be the result of the product of these 2. I'm going to times it by x squared, negative 2x plus 2. All right, now let's carry on. We're going to FOIL the first 2 pairs. When you FOIL these, you're going to get x cubed plus x. That's FO. The I is negative 2x squared and the L is negative 2. And that multiplies by x squared, negative 2x plus 2. Okay. Now, let's distribute this. Okay, therefore, f of x is equal to, I'm going to distribute x times these 3, x cubed. Then I'm going to distribute x times those 3, then negative 2x squared times those 3, then negative 2 times those 3. That's exactly what we're about to do. So let's do x cubed times these 3. X cubed, x squared, that will be x to the 5th. Next one would be negative 2x to the 4th plus 2x cubed, right? That's the first distribution. The second distribution is when you do x times all 3 of those, right? Each of them. Now, instead of writing them in a horizontal format like this and have one long line, I'm going to write this product in a vertical format. In vertical format, it's going to be more concise, and it's also, more importantly, it's going to help me combine like terms a little easier. Okay, so let's do it that way. X times x squared, first distribution. See right in here, I'm using the column format. That's x cubed. Then x times negative 2x is negative 2x squared. X times 2 is plus 2x. Done with that distribution. Next, let's distribute negative 2 times these 3. Negative 2x squared and x squared, that's going to be negative 2x to the 4th, right? Plus, next is going to be positive 4x cubed. Then it's going to be negative 2 times 2x squared, so that's negative 4x squared. Correct? Got that one done. And then the last distribution, we're going to do 2 times each of those. So negative 2 times x squared is going to be negative 2x squared, right? And then negative 2 times negative 2 is positive 4x minus 4. And then we're going to add in columns. Bring down x to the 5th. Combining those, we get negative 4x to the 4th, right? Next, the x cubes are like terms. We got 7 of those. And then we got 8x squared plus 4 and 2 makes 6x minus 4. And there you have it. Oh boy, there you go. There is your 5th degree polynomial. Took a little while because the roots are complex, and this is a 5th degree polynomial. But here's the solution. This is what we wanted, and that is the answer to this problem. There is your 5th degree polynomial. Okay. Now, let's take a look at another example. Okay, in this next example, suppose, let's say my f of x is this time 4x to the 4th plus 7x cubed plus 62x squared plus 112x negative 32. Okay, now let's say 1, 0. 1, 0 is 4i. Suppose somehow we know that it's 4i. We want to find the remaining zeros. Okay, and let's see how this is going to work out. So by complex pair, conjugate pair theorem, by this one, because the coefficients are real and the polynomial, therefore, see, these numbers are real. So we can write the other zero. The other zero right off the bat is going to be negative 4i. So we got 2 out of 4. The other 2 we can find using quadratic formula, I'm sure. So let's write this. F of x is going to equal to, I'm going to write it as parentheses x minus 4i, and then x plus 4i, right? And then we have x minus the 3rd root and x minus the 4th root. Okay, now the leading term is 4, so I'm going to put 4 in here. All right, let's carry on, and we can actually again leave the 4 if you want. We can leave this 4 out, but I went ahead and wrote it in. Okay, now so this is going to be 4. Now let's multiply those conjugates. When we multiply these conjugates, what are we going to get? just square the first one plus square the number. So that's x squared plus 16, and then x minus the third root, x minus the fourth root in here, correct? So now what is this going to look like? Let's see. I need to, again, this I expect to get a second degree polynomial in here. So let's do a long division of the original polynomial, 4x4 plus 7x cubed plus 62x squared plus 112x minus 32. Let's do a long division of that by x squared plus 16. Okay, let's do that. So how is this going to go? Well, we're going to divide first term by first term, right, in our long division. We cannot do synthetic division, by the way, because that's x squared plus 16. It only works with x minus c. Synthetic division has to be by a binomial, like that. So you're going to divide 4x4 divided by x squared. And what do we get? We get 4x squared, right? 4x squared. That's the first term in the quotient, 4x squared. Then multiply by x squared, we get 4x4 plus 4 times 16 is 64x squared. And then we're going to change sign on these and add them. Okay, so I'm going to have 7x cubed negative 2x squared plus 112x minus 32. And we continue on this time. First term in the quotient, in the dividend, divide by first term in the divisor, and that will be 7x. This is the next term in the quotient, 7x. Okay, and we're going to multiply 7x times divisor. That will make it 7x cubed. And 7 times 16, that's 112x plus 112x. Okay, and then we change sign on these and add them. So that's now going to be negative 2x squared minus 32. And finally divide negative 2x squared by x squared. We get negative 2. And that's minus 2. Negative 2 multiply this times the divisor. Negative 2 times x squared is negative 2x squared. Negative 2 times 16 is negative 32. And then we're going to change sign and add them. The remainder is 0. Perfect. So there is the other polynomial. Or if you want, you can do rational zero theorem and go from there. Okay. Now, I'm going to leave this 4 out because the way I did this, see, I worked with the original polynomial and this is what I got. Okay. And I'll show you, I can factor the 4 later on. This is what we have. This is the leading coefficient, right? I'll show you how that can work in the end. Outside of the whole action, outside the parentheses and in front, okay? We will have that 4 in front in just a moment. So at this point, I have x squared plus 16, and then times the quotient 4x squared plus 7x minus 2. You see that? That's the polynomial. So let's find now the zeros here. We already have 2 zeros coming out of x squared plus 16, right? 4 and negative 4i. Let's factor this further. The factored form of 4x squared plus 7x minus 2 is going to be 4x minus 1 times x plus 2. Okay. Now, the coefficients, by the way, the coefficient on x is 1 here, and here it's 4. So from the binomial, and this is where I'm going to make it look like the leading coefficient of 4. From this binomial, I'm going to factor a 4. So now there's 4 in front. Okay. X squared plus 16 doesn't change. When you factor a 4 from 4x, we're going to have x. Factor the 4 from 1, we're going to get 1/4 and x plus 2, and there you have it. So that would be the full factored form of that polynomial. And from this, we can get the zeros, the other two zeros now very easily. X minus 1/4 is 0, so x is 1/4. And x plus 2 is 0, so the other real 0 is -2. And we have all zeros now. Therefore, the zeros, the collective zeros for this exercise is going to be plus or minus 4i, and then we have -2 and 1/4. And what you're looking at here actually is a full factored form in standard form, right? And there you go. Again, we didn't want to do anything else. We just want to find the zeros here, and we found all zeros, all 4 zeros. Okay. And with that, we are done with this section and with this very long chapter that had they had 7 sections. So we did quite a bit. And I still managed to keep this under an hour. Okay, everyone. Thank you for watching, and hope you enjoy the video. And please, if there's something that's not clear, watch the segments again. You don't have to watch all of these videos at the same time because they're too long, but they're necessary, right? This is good information that we need in order to do your homework and move forward. Okay, so feel free to pause, stop, come back, whatever. At any rate, thank you for watching, and until the next video, take care.